Hello everybody, I'm going to be doing some physics stuff right here. It's hard to know, the exact prerequisites for this. I guess you should know how to calculate energy, although I'm going to tell you, of an object. I don't know, you should maybe know what the dot product is with two vectors. That would be helpful. Pythagoras theorem, just basic algebra, and what I'm going to be showing today is how to do 2D circle collisions. So if you have two circular objects and they're two-dimensional and you want to know what their velocity should be after a collision so that the energy before and afterwards is the exact same. So I'm trying to do basically a perfectly elastic collision where no energy is lost. And the thing is, the way that you do that, when you have a collision with two objects, I'm just going to do this in one dimension at first, okay? So when you have these two objects here, and they collide, they will apply a force on each other, and it will be the exact same amount in that direction as it is backwards. So if I were to just draw the force vector, they would be the exact same magnitude in both the directions, but they would cancel each other out. So if you apply any old force, then the momentum will guaranteed to be conserved. And this is Newton's third law, the fact that they're in the opposite direction and the same magnitude. That's Newton's third law. So anyway, just according to Newton's third law, you can apply a force on both of these balls so that momentum isn't conserved. So if you just applied any old force between these two balls, then it's possible that if you made it too small, the energy afterwards would be less than it was when it came in. But if you applied a force that was too great between these two balls here, then the energy afterwards would be too much. It would be higher than it came in. So I'm trying to calculate the exact force that we need to apply so that after the collision, these two balls have the exact same total energy. And this is how you figure it out. So first, it would be nice to know what the energy at the beginning is. And we know the equation for kinetic energy is 1/2 times the mass of the object times the velocity of the object squared. So for this object right here, its mass is 4, and 3 squared is 9, so 4 times 9, but it's divided by 2, so it's 2 times 9. So the kinetic energy of the first object is 18. Whereas this one, it's 2 squared times 1 divided by 2, which is 2. So 18 plus 2, the total kinetic energy at the beginning, with this system here, is 20 joules. But as you can see in the future, this one's going faster than this one, so this one's going to collide into this one, and I want to see what the velocity afterward should be. So I wrote this equation here, and I didn't know that it would be, I'd be able to even solve it, but as you can see, it says that this is the energy of the first object, 1/2 times m1, the first mass, and v1 is the first velocity. The initial velocity of the first object, so v1 squared, plus the energy of the other one, so I just put 2's there, should be equal to the energy afterwards. So the energy afterwards, the mass doesn't change. It's still m1 and m2, still the 1/2 there and whatever. But now the velocity has changed. Now the velocity would be what it was before minus some force over the mass, because a force over mass is acceleration. So it's an acceleration, it's a velocity minus the acceleration. Normally you would be putting a t here, so that this would be like impulse, but I'm just leaving it out because it's like an instantaneous collision. It would be more correct if I basically replaced all these f's with p's for momentum. Because momentum over mass is a velocity, so if you can subtract two velocities and get a velocity. And basically what I'm trying to do is figure out what the final velocity is if you applied a force on it. And this one I subtract the force, whereas this one here I add the force because you have to do it in the opposite direction. So v squared plus f over its mass, because the greater the mass of the second one, the less the second velocity is to accelerate. So this is the equation that I wrote down. And yes, I actually do notice that it's incorrect because I made it a while ago before I noticed that I totally should have just put impulse here. But now everything has an F, a force, instead of impulse. So what are you going to do? It's sort of incorrect, but it still gets me the right answer. I'll show you. So if you have m1 here and mv squared, I basically just got this equation up here, and I multiplied all of the terms by 2, and that's allowed. So this is still true, this equation here. Now it has all those 1/2s gone. So m1 v1 squared plus that is equal to this. That's some algebra right there. And I continue here. Here what I do is I expand this binomial by using, what's the equation? It's like this. It's like a plus b squared. You can just use a triangle to figure this out, but I'm just going to write it down just so you know. This is just math. 2ab plus b squared. So I use that here, and I expanded this. See, it's squared, and now it's not squared. And I expanded this binomial here, so it looks like that now. Whee! That's cool, and I did the exact same thing over here with the second part, the second energy. Okay, fantastic. I go to the next step, which is where I factor in the m1 and the m2. So, well, I expand by multiplying every term inside these brackets by m1. So now it's m1 v1 squared, and then it's m1, and it cancels out with the m1 here, so it's just negative 2vf right there. And then it's m1 times this one, but here the m1 was squared at the bottom, so now it's just not squared. Cancels out a little bit. And I do the exact same thing over here. So m squared. Now this is the great part. When I was just doing this math for the first time, you'll notice that this is m2 v2 squared, and the exact same thing is on the other side of the equation. And they're both just two little terms. And if you know algebra stuff, what you can do is you can just subtract both sides of the equation by that and this and this and this, and you'd get left with a 0 on this side since I just subtracted it, both of the things. Oops. Anyway, so you end up with 0 on this side. And this side, now we don't have the mv squared, so it's just negative 2f. This part, and you know, this part, and this part. But not these, because I subtracted them from both sides of the equation. So now the equation is a little bit smaller and nicer. And I forgot to mention, the whole point of this simplifying this equation is so that I can, like I said, I was trying to figure out the force that I need to apply on these two balls so that the energy is the same afterwards. So I'm actually trying to isolate for the letter F, okay? And as you can see, in every single one of these terms, there is an F. And that's to say that if we were to set F to 0, then this equation would be satisfied. It's true. So that means that if you apply 0 force on these two balls, then the energy will be the same afterwards. But I already know that. If you just don't apply any force, then the velocities won't change, nothing will change, the energy should stay the same. So I'm just going to factor out all those f's there. You can divide 0 by f and the whole thing by f. And this equation is still true over here. So now the f's gone from there. And I also, in the same step, factored out the 2 from v1 and v2. So it's 2 times v2 minus v1. Because this v1 is negative here and this one's positive, it's like that. I only factored the 2 from those two terms. But this one right here, f squared over m1, and f squared over m2 are still over here at the end. So that's great. Yeah. And remember, like I said, I'm still just trying to find f. So I move this part to the other side by subtracting it on both sides. And here we go, we get that. And then these are in the denominator. But what you can do is you can multiply the whole thing by m1 times m2. If I multiply both sides by m1 times m2, well, this side becomes, m1 and m2. That becomes one of the factors there. And then here, if you multiplied this part by m1 and m2, then the m2 would cancel out and it would just be m1. And the exact same thing would happen here in the reverse, so that it's f and m2 here because m1 cancels out. Fantastic. Now they're not in the denominator, so it's a little bit nicer. And if you were to factor this part right here, I could actually write it out here. Factor the f out of both m1 and m2, you would get this. And basically what I do is I divide both sides by m2 plus m1, and you get this equation right here. So, like I said before, this is actually the impulse, but it's sort of like a force. It's the amount that the velocity changes, but it's still dependent on the mass of the object. So, if it's a greater mass, then it'll, change speed less. So this right here is the equation for impulse. And you use this to calculate collisions. And I figured this out myself. I'm very good. So yeah, I guess it's kind of confusing to go back and forth between impulse and force, because the truth is it's really just impulse, not force. It's just the first time that I did this math, I didn't know and I wasn't thinking, and I happened to use force for every single place where there should have been an impulse symbol. Oh well. So here I do some extra math. I'm going to actually show you an example of it. And I'll show you the example using this first one here, the 1D collision, okay? So remember, the energy at the beginning was 20 joules. If this is in kilograms, if these masses are in kilograms and these velocities are in meters per second, then you'll get the energy out in joules. So, where is it? Okay, so if we use this equation here, 2m1 m2 times vf minus v1, you get the force that you have to apply on both of the balls. And you get 2 times m1 times m2. So m1 and m2 are 4 times 1 is just 4 times 2. So I'm writing it here, 2 times 4. 2 times this is 4, and then the difference in their velocity. So, did I write VF? That's wrong. I meant to write V. That's supposed to be V2. Oopsies. So basically the relative velocity of the two objects. As you can see, their relative velocity is 1. This one's only moving 1 meter a second slower than this one. And that means that they're going to collide with each other. So their relative velocity is 1. And their added masses is 5, because 4 plus 1 is 5. Yay! So this is the impulse or force or whatever that we should apply in both of the things. It's 8 over 5. So in order to find the acceleration on the first object, it's actually not an acceleration. It would be a change in velocity if you consider it as an impulse. Okay, so the change in velocity would be by 2/5. And the change in velocity for the second one would be by 8/5, because you divide it by the mass. So 8/5 divided by 1 is 8/5, and 8/5 divided by 4 is 2/5. So this is the change in velocity. And remember, you have to subtract it from this one and add it to this one, so that they're in the opposite direction. And the way I'm going to do that right here, the velocity of the first object here is 2. So we add that to the 8/5. So 2 plus 8/5 is the same as 10/5 plus 8/5, because 2 is 10/5. And if you do 10/5 plus 8/5, you get 18/5. Yay! And I do the exact same thing over here with the other one. Its velocity is 3 minus its change in velocity, 2/5. 3 minus 2/5 is 15/5 over minus 2/5. Which is 13/5. Yay, okay? So these are their final velocities for these two objects. And here's the greatest part. If you were to put that into the equation to find the total energy afterwards, you do 1/2 times the mass of the first object times its new velocity, which is now 13 5 squared. I did this all algebraically nice here. So it's 1/2 times 1 times 18 squared over 25. This is all basically math. I said that 18 squared is 9 squared times 2 squared. And I cancel out the 2 there. So that over here it's 81 times 2, which is 9 squared times 2, because those 2 cancel out there. And then on this side, you know, there's a 25 common denominator, so I just put it at the bottom, and 13 squared is 169, and the 4 cancels out with the 2, so it's just 2 times 169 plus this shit. And then you do this, 2 times 169 plus 81 times 2 over 25, which is 2 times 16. I factored out the 2 to make it a little easier for me. So it's 2 times 250. This adds up to 250 very nicely. And then the 25 cancels out with that 250, so it's 2 times 10, which is 20 joules. Oh my god. You thought these ugly velocities here might not get you the right energy afterwards, but they do. We get the exact same energy afterwards, 20 joules, as we did coming in. The initial energy is 20 joules. Conservation of energy, and it works, dog. All you need is this simple equation here. It's fantastic. So when you consider 2D collisions, let's say these two balls are moving this way. Oh, what the heck happened? Like that. They're moving upwards, but they're also moving this way. And what basically we have to do, so their vectors are like this, and they're velocity vectors, and we just have to consider how much are these velocity vectors on the same axis? How much are they traveling into each other? And to figure that out, you have to use the dot product. So, I'm not going to get into that right away, but I'm basically just saying that this velocity right here and this velocity, you just get the difference between that, and then you can plug those values into this equation to get the force that you should apply that way and that way on these two balls. And you can just totally ignore the fact that they're both moving upwards at the same time, okay? So you just have to consider that they're moving upwards at the same time, but they're still just colliding linearly. They always collide on only one dimension. So there you go, there's that. And here's an example where I wanted to show you what it looked like if there was 2 dimensions. And if you use 2 dimensions, and I'm just going to use vectors. Vectors with, you know, an x component and a y component. So here are 2 masses, 3 and 4, and as you can see, they're kind of colliding in a funky way. I'm saying that the distance between their 2 points in the middle there is 1. So that's 1, and that's 1 right there. This distance is 1. So they're like kind of 45, this is a 45-degree angle, sort of. They're colliding like that. And this object, this ball here is moving at, how fast is it moving? Oh, it's moving -1 in the x direction and 0 in the y direction. And this one's going 3 and 3, so it's going 3 that way and 3 that way. Great. Okay, so these are your 2 equations. These are your 2 masses and their 2 velocities. And this is not so easy to just plug into this equation right away. 2m1 m2 equals the impulse. So how do you figure out what you actually have to put into there? And there's actually kind of a bit of tricky math-ish. I figured it out. I managed to figure it out, so that's cool. What do I have to show now? Where is it? So here are their velocities, but you have to consider that the force that's going to be applied on these 2 balls, since their distance is like at this 45-degree angle, that's their difference in position, is like this 45-degree thing. That is the direction that the force is going to be acting on, as in this ball is going to get the force in that direction, and this ball is going to be get the force in that direction. Along this one dimension right here that they collide on. That's where the velocity, that's where it all matters, okay? So, what I end up having to do, if you know anything about normalizing, it's when I'm first going to normalize the distance. So the distance is 1 and 1, as in this one is 1 over to the x and 1 over in the y. The distance is 1, 1, And if you normalize this vector, which means to make its magnitude 1, to make the size of this vector 1, so that it's basically just retaining the direction of the vector. The way you do that is you divide the whole vector by its magnitude. So what's the magnitude of a vector with 1 and 1? Well, you can use Pythagoras' theorem, and it's 1 squared plus 1 squared, the square root of that, and that's the square root of 2. Okay, so the magnitude of the distance is the square root of 2. However, the magnitude of the distance has nothing to do with what it's going to be. So like I said, you have to divide away that so that it's just the direction. It only retains the direction of the dot of the distance. Why? So that we can dot product it with the velocity. So I'm just going to do it. If you divide the distance by its magnitude, the square root of 2, then it's 1 over the square root of 2 and 1 over the square root of 2. So I'm going to call it normal, and I'm going to say the normal is 1 over the square root of 2 and 1 over the square root of 2. The normal has, a size of 1. So if you were ever to do a dot product with it, the, the result of the dot product will only be really proportional to the second vector that you put in. The first one will have a magnitude of 1, so no matter what you multiply it by, it's going to just only, for example, if you multiply 5 times 1, you still get 1. So here's the equation for the dot product. It says that the more the angle is 0, as you know, cos of 0 is 1. So the more this is, wow, I'm really getting off track here. I'm not going to try and tell you what the dot product is because that sounds like something that would take a little bit of explaining. But basically, you do the dot product of the first velocity and the normal and the second velocity of the normal. And what that's supposed to tell you is how much these velocities are going into each other, how much they're going on this axis. So as you can see, this one looks like it's going on this axis like a lot. They're pretty much in the exact same direction. In fact, they are in the exact same direction. And this one, as you can see, is kind of moving in the opposite direction a little bit, but off to an angle. So if you do the dot product of this normal and the two velocities, and this is taking so long. Anyway, 3 and 3. This is how you do the dot product with the vector. You multiply the two x components, which is 1 over the square root of 2 times 3, plus 1 over the square root of 2 times 3, because that's the second part as well. That's the y component. So you multiply the x components and the y components, you add them together, and you get 6 over the square root of 2. And that is exactly how much this velocity is moving in this direction. And this is the same thing for this other velocity. As you can see, it's negative 1 over the square root of 2, because, like I said, this one's moving in the opposite direction of the distance vector. So it's going to be negative because it's negative, dog, okay? And when it's negative, the dot product is negative when they're in the opposite direction. That's one of the things about the dot product. Because the angle between them would be greater than 90 degrees, and as we know, cos of, say, 100 degrees is going to be a negative value. So I have these two numbers, and that's how much these two objects are moving along this axis here. Oh my god. And if you subtract them, you get the relative velocity. What's their relative velocity moving across this axis here, okay? So how much they're basically going towards each other on that axis, how much you're going to touch right at this point here. And you get negative 7 over the square root of 2. So that means that negative means they're moving towards each other. Positive would mean they're moving away from each other. And as you can see, they're clearly moving towards each other, so it's a negative 7. Okay, so that's actually all you need to do. Once you figured out negative 7 over the square root of 2, which is how much they're traveling into each other, you get to just plug that into the equation. It's fantastic. You do negative 2 because that's what the equation says up here. Where is it? We're going to use this equation here, 2m1 m2 over v squared. You know, just memorize this part, okay? Because I'm using it right here, way down here. 2 times the masses of both of the things, 2 times 3 times 4, times their relative velocity, which is -7 over the square root of 2. Remember, that's the both of the masses velocities subtracted by each other, which I already did here. And then you divide it by their total mass, and we get 24 over the square root of 2. Okay, so that's the impulse that you should apply on these two balls here. But remember that impulse, you have to apply it in opposite directions like this, and along this vector right here. So since this vector is a normal, 1 over the square root of 2, it's nice because you get to multiply magnitude times it. If you multiply, I'll just give an example. If this unit length is 1, this arrow here is 1, and you multiply it by 2, you get a vector with the exact size that you'd like, 2, and you get it in the exact same direction as that normal. So you get to use the normal as a directing thing, and you get to use the magnitude because, you know, that's the amount that you'd like to push it by. Okay. So, in order to figure out the force, oh god. So yeah, as we know, acceleration is equal to F over m, or the change in velocity, delta v, I don't know, equals P over m. These are the same things, like I'm saying I use the F instead of the P over m, and the acceleration instead of change in velocity. Even though they're actually very technically different things, I managed to figure out all this stuff using the wrong math. Anyway, cool. Wrong physics, at least. So here's the normal. If you multiply remember I said if you multiply the factor times the normal, it just puts that size in the normal's direction. And I use a negative normal here because it has to go in the negative normal direction, and for the other one, it goes in the positive normal direction. It goes that way, and we're trying to apply that force on this ball. Just intuitively know that the force is going to be that way for this ball, and the force is going to be that way for this ball. So a negative normal here, and we do 8 over the square root of 2 times a negative normal. Now that's nice because the square root of 2 doesn't cancel out, but it multiplies with the square root of 2 in the normal, 1 over the square root of 2. So 8 over the square root of 2 times 1 over the square root of 2 for the x part is -4, because this is a -4, this is a negative right here. So 4, -4, shit like that. And here we got the here we got the change in velocity for the second mass. Holy crap. Remember, these are the labels for this is the second mass, this is the first mass. I never said that. That's the one. That's the second ball. So these are the change in velocities. So if you add these vectors with their velocity vectors, oh my god. So you do, since this is the initial velocity was 3 and 3, you add that to -4 and -4. So 3 plus -4 and 3 plus -4. The final velocity of this one right here is -1 and -1. And for the other velocity, I do the exact same thing. I add 3 and 3, which is this one over here, the change in velocity for the second object. -1 and 0 plus 3 plus 3, you know, shit like that. It's 2 and 3. So the velocity of this one afterwards will be 2 and 3. If you were to find the magnitude, I think I already did it. I'm actually going to show you that it works, okay? Which seems kind of like too far to do, but I'm going to do it anyway. So you have -1 and -1. Oh my god. Here I find the oh my god. I find the magnitude of the first velocity, the initial first velocity. Remember it was 3 and 3. So 3 squared plus 3 squared is 9 plus 9 equals a square root of 18, and so that's the magnitude of this velocity right here. And so therefore the energy with that is its mass times 1/2 times the velocity squared. So it basically gets rid of that square root right there. So you just do 18. Oh, I simplified it so it's 3 times the square root of 2. 18. The square root of 18 is 3 times the square root of 2. I find the energy of that. The energy of the first ball initially is 27. The energy of the second ball initially is, I use a Pythagoras theorem. Oh my god, it's 2 joules. So this ball here had 2 joules to begin with, and the other one had 27. So, oh my goodness, that adds up to 29 joules, okay? So the 29 joules were before, and if you use these new velocities afterwards, the 2 and 3 and -1 and -1, and you do the exact same thing and you calculate the energy, instead of getting 2 and 27, you would get 3 and 26. That's interesting how it transferred exactly 1 joule to the other object. Oh, didn't mean to do that. Oh, shit. Just give me a second here. Interesting how, yeah, it transfers exactly 1 joule to the other ball. But yeah, I created this method here. It might be convoluted, I don't really know. It's what I use to do collisions in my program. I have a program that does 2D collisions with balls, and it works like a charm. So I think that'll actually just be enough for the video. I mean, I kind of took it on along a bit, and I showed a lot of examples, and I probably poorly explained it. But I hope you guys get this shit. It's 26 plus 3 is also 29. And we got the same velocity, same energy before and afterwards. Even though I did all this convoluted 2D stuff. And yeah, you can even do this on 3 dimensions because, like I said, all the collisions all only happen in 1 dimension. So, there's some great stuff. I think I did even more math. Wait. No, not that I really need to show any more math. There's been enough here. Oh yeah, here's a little equation that I wrote here, just to wrap my head around some things. There's the final velocity is the initial velocity, plus the impulse over the mass. So this whole time, I've been saying this final velocity equals the initial velocity plus acceleration, basically. But as we know, or as you might know, it's actually supposed to be AT. And once you put the AT there, once you put the T there, you have to consider that it's not really a force, it's an impulse. And an impulse is really, it's a force over a time, right? If you do force times time, you get momentum. So momentum is not only just mass times velocity, it's force times time. Or a force integrated over time. Which is another helpful way of thinking of what momentum really is. It means that if you divide it by the amount of time that it took to apply that force, you would get, you would just get the force. Wait, what the heck? Yeah. Anyway, I'm sorry if I didn't explain it to as clearly as I possibly could. Apparently I'm not the best explainer, but I really hope this was helpful somehow. If somebody was trying to do 2D collisions and they somehow needed my help. I'm done this video. So, good luck.